as always. All right, Organic Chemistry 2, Chemistry 3111. This is Chapter 21, which deals with alpha carbon chemistry, enols, and enolates. And enols aren't unfamiliar to you. This is something that you would have seen earlier on in this class, but we're going to talk about enolates, which is, something that's new to us in Organic Chemistry 2. So here's our introduction, enols and enolates. The first thing we need to discuss are Greek letters because we're going to use them a lot in this chapter. It says that Greek letters can be used to describe the proximity of carbons relative to a carbonyl group, right? You know that a carbonyl is when we have a carbon with a double bond to an oxygen like that. That's what we call the carbonyl group. I'll highlight it in green here. So as we get away from the carbonyl carbon, which would be this carbon right here that I'm writing in green, well, as we go away, we use Greek letters to label those carbons. So we have, as you can see here, we have 2 alpha carbons, we have 2 beta carbons, we have a gamma carbon, another one here, and then we even have a delta carbon on that side of this ketone. So what we're going to talk about most of the time in this class will be alpha carbons. We'll be really concerned with alpha carbons in this chapter. So again, alpha carbons are the carbons that are directly adjacent to the carbon of a carbonyl group. Well, what makes alpha protons that are attached to an alpha carbon so special? Well, the thing is that if we take a carbonyl compound that has an alpha carbon and it has alpha protons, so again, alpha protons are those protons on that alpha carbon, whether you put the carbonyl compound in a catalytic acid or base, you can end up making the enol tautomer. So again, you've got to have alpha protons, and obviously there's a total of 6 alpha protons, right? There's 3 on this side, there's 3 on the other side. So when you have those alpha protons, whether you put the compound in acid or base, you can produce an enol, all right? And if you take an alpha carbon compound with alpha protons, like acetone here, if you put it in strong base, you can make what's called an enolate. And you could probably draw the mechanism of the enolate formation. You could probably guess that, you have the alpha proton here. If you have a strong base, it can rip that proton off and form your enolate like that. And we'll look more at that mechanism later on. But what we're even more concerned with is that most of the reactions that are covered in Chapter 21 are going to proceed either through an enol intermediate or an enolate intermediate. So what we're going to do is, you can see here that whether we have an enol or an enolate, that we can introduce functionality. So that's what X represents. It doesn't necessarily always represent a halogen, but we can introduce functionality at an alpha carbon. So let's talk a little bit more about enols. Now, enols are an enol rather is a tautomer of a ketone, right? We saw this before, that if you take the ketone and you put it in a catalytic amount of acid or base, that we can have that enol in equilibrium with the aldehyde or the ketone. Keep in mind, these are not resonance structures of each other, okay? It's got nothing to do with resonance structures. These are actually individual molecules, the ketone and the enol, but they're in equilibrium with one another. And again, we don't call them, they're not resonance structures. It's got nothing to do with that. We call them tautomers. Now, tautomers differ in that they are molecules that are isomers of one another. However, they differ in the placement of a pi bond, okay? And they differ in the placement of a hydrogen atom, right? You can see that this pi bond is now here in the tautomer, and you can see that one of the hydrogens that was here is now up here on the enol form, okay? So that's what tautomers are. Now, if you look at a ketone like cyclohexanone, which is shown here, you see that it's mostly in the keto, what we call the keto form. So this is what we would call the keto form. But you can see that the keto form, or the ketone, you could say, it predominates, okay? It's mostly the ketone, and there's only a small amount of the enol in equilibrium with that ketone, but that's not always going to be the case, okay? It's not always the case. There are exceptions. This is what we call a 1,3-diketone, or a beta-diketone sometimes. I'll put it here, beta-diketone, okay? Because if this is your alpha carbon, here's your beta, and then you have a carbonyl, so you call it a beta-diketone or a 1,3-diketone. But check this out. Here's an enol right here inside of our diketone. And if you look at the equilibrium, it actually favors the enol. Okay, it's mostly favoring the enol. Now you can probably guess why. There's two good reasons why the enol form is favored. Number one is that there's conjugation. You remember conjugation? It means when you have double, single, double, single, double, single, alternating like that. That introduces a stability to the enol form in this case. And then you can probably even more obviously tell from the drawing here that there's a beautiful hydrogen bond between a lone pair on that delta negative oxygen and the delta plus hydrogen, right? There's a hydrogen bond here. So this is a hydrogen bond. So it's kind of a double whammy in this specific case of this 1,3 diketone or this beta diketone. So again, this is an exception, right? It even says it right here. This is an exception. I can show you an even better exception. I don't know if it's better, but an exception where the enol definitely predominates, and that would be when we have phenol, right? Everybody who's hearing the sound of my voice could draw the structure of phenol. It's this molecule here. It's got a pK of around 10. Well, if you look at phenol, you notice that there's an enol inside of phenol. You can even see the enol is in the name phenol, right? But anyhow, if you look at the keto form, you see that it actually exists, a very little amount. Why? Because when we have the keto form, we don't have the aromatic stability, right? But here in phenol, we have the aromatic ring intact. And so this is a really neat example where the enol is vastly favored over the keto form at equilibrium. Well, let's talk a little bit more about the reactivity of carbonyls and how we form enols and enolates. You will be expected to know how to draw the mechanism for the formation of an enol or an enolate. So for an enol, first of all, from a ketone or an aldehyde in acid or base. So first we're going to start by looking at acidic conditions. Good news, just 2 steps. Okay, the first step is if we're in acidic conditions, what does that mean? We've got hydronium, right? So if we're in acid, the first step is going to be a proton transfer from our hydronium. Now we've rendered this really electrophilic. You can see that through this resonance contributor here. Then we just do a proton transfer, right? We rip off one of the alpha protons, and there you go. Now we have our enol like that. So that's the conversion of a ketone. And you could do the same thing for an aldehyde, same mechanism, but to the enol in acidic conditions. We could also do it in basic conditions. This is tautomerization just in basic conditions. Right? What does that mean? We've got hydroxide kicking around. So if we have hydroxide, what's that going to do? That's going to rip off an alpha proton first. It makes what's called an enolate, and we're going to talk more about enolates later on. But you see how there's 2 contributors to the overall resonance hybrid of the enolate. And then the oxygen is going to rip off a proton off of water, and there you have it. You have your enol. So again, we go from the keto form to the enol form. Right, and if you haven't figured this out already, and I might have mentioned it in a previous lecture, but where does the word enol come from, right? You've got an alkene in the molecule, and you've also got an alcohol, both in the same molecule. And I'm sure that most of you connected the dots on that way ahead of time. Well, let's talk a little bit more about enols, and let's talk about the reactivity of enols. All right, if you actually look at the structure of an enol, I'm sure if I was to ask anybody here, if I said, here's a beautiful enol, I want you to draw its resonance structure, I know that you could all draw this resonance contributor here. But if we look at this resonance contributor, we know what information do we get from this? We see that the alpha carbon, right, the alpha position is nucleophilic, right? Because in this resonance contributor, it's got a negative charge on it. I can go one more for you. Look at the electrostatic potential map. Right, this is the EPM, the electrostatic potential map. We use them throughout the class. And you can see that, the red areas are electron rich. And you can see there's a lot of electron density up on the oxygen, which is more electronegative than any other element in the molecule. But you notice that there's quite a bit of red down here by this carbon. That tells you that it's electron rich. And therefore, that alpha position of your enol is going to be nucleophilic. Okay, well, that's kind of interesting. Now, I bet you I know what you're thinking. You're thinking, well, I bet you that an enolate is even more nucleophilic, right? Because we saw that, and I showed you this mechanism a few slides ago, and then I deleted it because I said we were going to show it later. But if you take a strong base and it rips off an alpha proton, you get an enolate, right? And again, this is one of those circumstances where I know everybody who's hearing the sound of my voice could draw these two resonance contributors for an enolate, right? Not an enol, but an enolate, right? 8. Think about 8 in chemistry. What does 8 mean? 8 means a negative charge, right? Sulfate, nitrate, carbonate, chlorate, perchlorate, enolate. So it's got a negative charge overall. Well, you bet your bobby socks, this is nucleophilic, isn't it? Right? You see, we've got a negative charge on the carbon in this resonance contributor, and then we get a negative charge on the oxygen up here. So it says here, the enolate is much more nucleophilic than an enol because it has an overall negative charge, right? Go back to the enol, okay? The enol isn't negative overall because whenever you have the negative, it's balanced out by a positive, right? Overall, the enol is neutral. It's just telling us that the carbon is nucleophilic, but when you have an enolate, oh boy, that's going to be really nucleophilic, right? Because it's got a negative charge, right? We could even write that on here, 8, remember, anion in chemistry class. All right, there you go. So enols and enolates, and we're going to see how we can use enols and enolates all the time in this class. Well, if you look at these two resonance contributors for your enolate, you notice that one of them has the negative charge on the carbon, one of them has the negative charge on an oxygen. Well, if I know enough about organic chemistry, I know that I've seen nucleophiles in this class many times where the negative charge was on a carbon, a Grignard, a cyanide maybe. And I've seen many nucleophiles like an alkoxide where the negative charge is on an oxygen. So, if I was to treat the enolate with an electrophile, where's it going to react? Would it react to the carbon or the oxygen? Well, let me show you what the answer to that is. If we go over here, it says the enolate can actually undergo carbon attack and oxygen attack. So both sides can act as nucleophiles, or both atoms, I should say, right? The oxygen with the negative charge, that can act as a nucleophile if it's in the presence of an electrophile. The same thing here, the alpha carbon with the negative charge, that can act as a nucleophile as well. Now, for this class in particular, for our class, Organic Chemistry 2, we're generally going to be looking at enolates undergoing C attack. Okay, both can happen. Okay, both can happen. It depends on the situation, but what we're mostly concerned with in this chapter would be carbon attack. So when it comes to drawing the mechanism of a nucleophilic attack, and that's what's being represented here, right? This is just a nucleophilic attack, right? This is my nucleophile, this is my electrophile. Well, there's actually two ways we could draw that mechanism. We could draw it the way it's shown here, which is what's shown here below, or you could just start with the negative charge up on the oxygen, and then you can draw the first curved arrow showing the formation of the pi bond, and then you can draw the second arrow showing the pi bond creating a new bond to the electrophile. Now, why would, personally, I like to use this more. Personally, I do. Now, why would we want to do that more? Maybe. Okay. And again, there's nothing wrong with this either. Okay. Why would I want to do this more? Maybe because, if you think about the overall resonance hybrid, right? If we back up, where was it? Over here, in both of these resonance contributors, all of the elements have a complete octet, so that's no big deal. But in this one, oxygen is a more electronegative element than carbon, so we might think that this would contribute more to the overall resonance hybrid. So that's why I like the first way here the way on the bottom left down here. Okay, but most of the reactions, in this chapter are going to involve enolates. We're going to look at a heck of a lot of enolate chemistry in this chapter, and we're going to see this mechanism come up over and over and over again. Okay. Well, again, a little more about those alpha protons. Just before we get too far and we start slinging arrows around and looking at all kinds of reactions here, the alpha protons are the only acidic protons on an aldehyde or a ketone that are going to be removed to form an enolate. Right? The reason why beta or gamma protons are not going to be deprotonated is because they're not acidic, right? If you were to rip off, let's say, this proton, you don't generate a resonance stabilized compound right? I mean, don't draw this. Please do not draw this. And I'm going to delete this. I might even have to edit my YouTube video because it just feels creepy. But you would never see this, right? Because it's not resonance stabilized. However, if the base rips off one of the alpha protons, and I'm just repeating what you've seen already, right? If your base rips off one of these, right, then you end up with this. Okay, so you end up with this where you have a negative charge here, but you have a resonance contributor, don't you? Where you can draw the enolate like this. Okay, so that is why we're only, oops, I don't know why I'm drawing it like that, but that's why we're only gonna, deprotonate at the alpha position. There we go, that's a little better like that. Okay, and these again are resonance contributors. Okay, so no deprotonation at beta, gamma, or delta protons if they're there. Okay, well, let's talk about, what would our base be? Right, I just threw up, some generic base. What is that base? What base would you use to deprotonate an aldehyde or a ketone at the alpha position to make an enolate? Let's take a look here. The first thing we want to think about if we're choosing a base is pKa value. Okay, the pKa value of an alpha proton of our aldehyde or a ketone has to be taken into consideration. If you take a look at some common ketones and aldehydes, right? Start with acetone. That's just good old nail polish remover. It's got a pKa of around 19. Acetophenone, way back in the aromatic electrophilic aromatic substitution chapter, I asked you to memorize the structure of acetophenone. It's got a pKa of around 18. And then if you look at acetaldehyde, so this is, the second simplest aldehyde. You go from formaldehyde to acetaldehyde to propionaldehyde, butyraldehyde, right? Anyhow, acetaldehyde is a pKa of around 17. So what's our range? It's in the neighborhood of, let's say, 17 to 19-ish. And I know it goes outside of that, but I'm saying it's in that range. Okay, so that's something to think of. Is our pKa of our alpha proton is going to be somewhere around 17 to 19. So we'll put here alpha proton pKa is somewhere between 17 and 19-ish. Okay, in that ballpark. Well, what would happen if we were to take, let's just start with acetaldehyde. There's the pKa right there. If we were to treat that with ethoxide, okay, it says right here, and I'm reading straight off the slide, it says when the pKa values of the base and the enolate are similar, both products and reactants are going to be present in significant amounts. So check this out. If you were to use ethoxide, okay, so this is my acid, right? This is my base. This is my conjugate base. And this is my conjugate acid. Come on. This is my conjugate acid right here. Well, if you compare the pK of the acid and the conjugate acid, I mean, they're not even a log unit, or no, they're a little more than a log unit apart. Okay, so what does that tell you? It tells you that you're going to have both the aldehyde in this case, and you'd have the enolate, right, in equilibrium. Now, the equilibrium is going to lie to the side of the weaker acid, right? That's why this arrow is bigger. However, we're still going to have both. So what does that mean? I mean, acetaldehyde, this molecule is a good electrophile, isn't it, right? Let me just draw it without any curved arrows on it, right? This molecule that I have drawn here, is that an electrophile? Heck yeah. Why not? Right? It's got a strong dipole going this way. This carbon is electrophilic. So if you put that in the presence of a good nucleophile, like a carbanion in our enolate, that's going to react. So that's the point that we're getting to. This is kind of an aha moment, if you will. In chapter 21, it says when the alkoxide is used, the enolate nucleophile can react with the ketone, or the aldehyde in this case. Okay, and that's what we're going to talk about in section 21.3. We're going to see all kinds of cases where an enolate will react with its protonated form, whether it's a ketone or an aldehyde. Okay, that's kind of where we're going here. Now, if you want to deprotonate all of your carbonyl compound to just completely make the enolate, right, no equilibrium, there's a few ways you can do that. Number one would be to use hydride, right? Something like sodium hydride, because hydride is not a good nucleophile. It's not polarizable, but it is a strong base. And if hydride would rip off a proton, then you form hydrogen gas. where is a gas going to go? A gas is going to go up into the atmosphere. So if we just draw, plus H2 gas over here, well, that's going to go up to the atmosphere. Based on Le Chatelier's principle, that's going to drive the reaction to completion. So that means that all you would have is the enolate left over. So that's total deprotonation. Another option is to use LDA. So LDA is an acronym you need to learn. It's lithium diisopropyl amide. Do you remember earlier on in Organic Chemistry 1 when we had NaNH2, right? It's Na plus and NH2 minus. I told you that NH2 minus was called amide, just like the functional group in amide. I know it's a little bit annoying sometimes when we use the same word to describe two things, but that's what we call an amide. So it's a nitrogen with a negative charge. So we take diisopropyl. See, there's two isopropyl groups on this amine. Then we treat it with a strong base, right? This is butylithium, okay? That's what this is. This is butylithium, right? We've got a butyl group with a negative charge, right? What's the conjugate acid of a butyl carbanion? It's going to be butane, which has a pK of 50. So you can imagine this is a crazy strong base, okay? It's a wicked strong base. So it's going to rip the proton off of diisopropylamine, which is just a liquid at room temperature, and you make this compound here, lithium diisopropyl amide. I'll tell you from firsthand experience, you can actually buy LDA in a bottle, okay? I wouldn't do it though, okay? You can actually buy a bottle that says, LDA on it. Again, I wouldn't do it because LDA tends to degrade pretty quickly. And so usually we make LDA in the lab. And that's why Dr. Klein actually went through the time to actually write this and put this in your textbook, because it's much more common to make it when you need it. You actually go and you get some diisopropylamine, you distill it, you treat it with some butylithium. So again, this is butyl lithium, and that gives you diisopropyl amide plus butane. Butane, from a Bic lighter is just a gas that goes up the smokestack, right? So there you go. Lithium diisopropyl amide. But what's the point here? Lithium diisopropyl amide, LDA, is a really strong base, and it's a terrible nucleophile because of these giant isopropyl groups. So if you take an aldehyde or a ketone with alpha protons and you treat it with LDA, okay? They left out the lithium anion, right? We love to do that in organic chemistry, don't we? It's here, right? So this is your LDA. Then you end up with the lithium enolate, okay? And you end up with this, which is diisopropyl amine. Well, check it out. If we just look at the pKa's here, you see that the pK of the acetaldehyde was around 16.7. What's the pK of an amine? 36? I mean, come on. It's a difference of almost 20 log units, 19.3 log units. So you can imagine this completely deprotonates everything. Okay? So again, what was the point? Is that LDA, I'll just redraw the structure here for you. So it's lithium diisopropyl. Okay, there's my lithium cation. Lithium diisopropyl amide has those two bulky isopropyl groups. So that is why LDA is a great, wonderful base. It is a horrible, horrible nucleophile. It's just too big and bulky to behave as a nucleophile. Well, what about the pK of that 1,3-dicarbonyl or that beta diketone that we looked at earlier? Remember that? Remember how we talked about this was, it's in equilibrium with a tautomer, the enol tautomer, and it's mostly the enol. Anyhow, well, if you have this compound, check this out. Look at the pK of these protons here, right? Because if you look at the beta dicarbonyl, right, this alpha proton is alpha to 2 carbonyls. So the pKa is lower by, quite a bit here. We're talking like what? Almost 8 log units compared to this, right? Why would that be? Well, I think if I was to ask anybody here, why do you think why these protons are so acidic compared to this alpha proton? I know you could all answer the question, right? It's because once you deprotonate and you form this carbanion, you have a dienolate, right? You could draw a resonance contributor where the negative charge is up on this oxygen or it's up on that oxygen. So again, think about acidity, right? Go right back to Organic Chemistry 1, first principles. Why is, sulfuric acid such a strong acid? Because the conjugate base is so stable, right? Why is this a stronger acid than this? Because the conjugate base is more stable, okay? You just end up with something that's more stable, well, then you've got a stronger acid, my friend. Okay, it's going to be a better proton donor. Now that we know the pK of the 1,3-dicarbonyl compound, check it out. What would happen if you treated that with sodium ethoxide? Okay, what would happen in that case? Well, check it out. If you were to treat that 1,3-dicarbonyl with ethoxide to make your enolate, okay, and you can draw the other two resonance contributors if you want, the conjugate acid that you end up with is ethanol, which has a pK of around 16. So now you have a difference in pKs of 9 and 16. So that's around what? 7 log units. Okay, so that's what? 10 million. So that means that this is 10 million times more acidic. So the equilibrium is going to lie to this side. So this is a specific case where you can actually take an enolate and you can completely deprotonate it using ethoxide. Okay, so in this case, again, when you have a 1,3-dicarbonyl, there's no need to use sodium hydride. There's no need to use LDA to make the enolate because it's overkill. Okay, it's just adding too much. Now, if you're thinking, why wouldn't I just use sodium hydride and just overkill it? Because then I know unequivocally, well, there probably are cases where people do that, but it's just never done in our textbook. So to summarize everything that we've covered in section 21.1, it's beautifully summarized on this table here. If you have an aldehyde or a ketone that's got an alpha carbon with alpha protons, you can partially deprotonate it using an alkoxide base or a hydroxide base. Sodium hydroxide, sodium methoxide, whatever. Okay, now you've got both of these present at equilibrium, and I told you the reason why that's so important is because when we get to section 21.3, you're going to see how this is going to react with that. We're not there yet, though, so I'm going to delete that. Okay, if you use that strong base, sodium hydride, or lithium disopropyl amide, LDA, you get complete deprotonation. And then, oops, son of a gun, didn't mean to do that. If you have a 1,3-dicarbonyl, so this is a 1,3-dicarbonyl. In that case, you can use those bases, those hydroxide or alkoxide bases, and you get pretty much complete deprotonation. Okay, there you have it, my friends. That is everything that we covered in section 21.1. Okay, what did we talk about? We talked about enols, we talked about enolates, we talked about briefly about how an enolate could behave as a nucleophile. It's mostly going to react at the carbon, not the oxygen, when it behaves as a nucleophile. And we talked about the bases that can be used to partially deprotonate an aldehyde or a ketone, the bases that can be used to completely deprotonate an aldehyde or a ketone. And then if you have a 1,3-dicarbonyl, we said, well, if you use an alkoxide or hydroxide base, that's still going to deprotonate everything. Why? Because these alpha protons are much more acidic than the alpha protons over here. And that's it. That's all. Well, with all that stuff in our brains, let's see if we can answer a question. This is question 21.6, comes straight out of your textbook. It says, draw the enolate ion that is formed when each of these compounds is treated with sodium ethoxide. In each case, draw all resonance structures of the enolate ion and predict whether a substantial amount of the starting ketone will be present together with the enolate at equilibrium. In the first one, you can all clearly see that there's, two planes of symmetry here. And so there's really only one type of alpha proton, whether you draw it there or if you draw it here, it doesn't matter. I'm going to draw it up here because it's just easier like that. So let's say it says if you're deprotonating this with sodium ethoxide, so let's draw, we've got sodium ethoxide, so I'll draw ethoxide like that. Let's draw the mechanism for the deprotonation. So we're going to rip off the proton, and then we're going to end up forming this enolate. So it's going to look like this. There's the negative charge on our carbon, and we're going to draw the resonance contributor. So there we go, where we have the negative charge up on the oxygen. So let's draw that. Okay, like this. There we go. Draw this carbonyl down here. And then, of course, we would also have ethanol. Okay, Well, remember that this is not a 1,3 dicarbonyl. Okay, this is a 1,4 dicarbonyl, right? 1, 2, 3, 4. So this can't take advantage of any other special resonance structure, right? So what does that mean? That means that we're going to have both of these at equilibrium, right? We're going to have this form, the normal form or the protonated form, and then we're going to have some of the enolate as well. So we'll write here both exist. Both exist at equilibrium. All right. Could anybody answer me and see how many types of alpha protons are there? How many different types of alpha protons are there? Is there one type of alpha proton? Two? Right. This is our carbonyl carbon here. There's an alpha carbon here and there's an alpha carbon here. But the alpha carbon on the left has no hydrogens attached to it. It's only the alpha carbon on the right that has a hydrogen attached to it. So that means that if we were to treat that with a base like sodium ethoxide, okay, draw my arrow like this to start with. We have our ethoxide. That's going to abstract the proton. Oops, I can make a prettier arrow than that. Like this. And then we're going to end up with this enolate. So first I'll draw it with the negative charge on the carbon, like that. And then we can draw the resonance contributor, like this. It's just going to look like this. And then, of course, we would have ethanol. All right. Well, again, this is not a 1,3 dicarbonyl compound. And so at equilibrium, we would we would have both of these present at equilibrium. So both present at equilibrium. Give me a thumbs up if you follow me on that. Is everybody with me on that one? Anybody there? All right, thanks, Courtney. I'm just going to go over to a blank slide here just for a second and ask you one more question. Okay, what if we had, let me get past all this. What if we had something that looked like this? So what if we had a compound that looked like this, okay, and we treated this with sodium ethoxide, okay? Well, we've got alpha protons here, and we have alpha protons like these ones in blue. Could anybody tell me which one of these protons would be more acidic? Would it be the one in red or the one in blue? And it's not a trick or anything. Yeah, absolutely. It's the one in red, right? Because it's part of a 1,3, right? 1, 2, 3 dicarbonyl system. So we would pull that one off preferentially, right? And we would end up with this, where we have the negative charge here. And now we can draw two resonance contributors, right? We can draw one where we put the negative charge up on the oxygen on the left-hand side. So it would look like this. Okay, so we're going like this. And then we could draw the second resonance contributor like this. So that's going to look like this, like that. There we go. And so this one is going to get completely deprotonated, right? Because this is going to have a pK of around 9, whereas over here we have our resonance contributors, plus we have ethanol, which has a pK of around, what was it, 16 or something like that, 16.7, okay? So we'll say here almost all deprotonated. There we go. So that's another good practice problem right there. And this is, again, this would be considered a 1,3 dicarbonyl or a beta diketone, either way. All right, let's go back to our slides. Where am I here? Chapter 21. Find out where I was. I was somewhere around here. So let's take a look at section 21.2. I'll be straight up with you. There's some reactions in here that you're probably going to have to memorize, kind of outright, because they only come up in this chapter. And there are some mechanisms that are important in this section, but there's a couple where the mechanisms aren't as important, and I'll point that out to you as we go along here. So we saw that when you take a ketone or an aldehyde that has alpha protons, and if you put it in acid, that you form an enol, don't you? Right? We said, okay, well, if you take, a ketone like this and you put it in acid, you would end up with the enol like that. Okay. Well, what happens is if you take a ketone like cyclohexanone and you treat it with a catalytic amount of acid, but you put some bromine in there, what you get is bromination at the alpha position. We call this alpha halogenation, and it works with chlorine, bromine, or iodine. It does not work with fluorine. Now, again, as I started out, when I first turned to this slide, the first thing I said was that if you're in acidic conditions, it means you've got the enol, right? Okay, because in acidic conditions, you have the two tautomers in existence. So let's take a look at what the mechanism would look like. And of course, the first step is going to be enol formation. So this is something we've already seen. How do you form the enol in acid? You do a proton transfer to render the carbonyl even more electrophilic. Okay, and then you can draw a resonance contributor here where you have the positive charge on the carbon, and you do another proton transfer, and you end up with the enol. Now here's the new chemistry, and it's these two steps right here. So we see how our bromine is polarized, so you get your delta plus and your delta minus over here, and now your enol is going to do a nucleophilic attack on the bromine. You lose bromide, and then another molecule of water, which was in your reaction mixture, is going to come up and do a proton transfer. So you're going to end up with hydronium, right, and bromide also at the end. Right? Notice you're not ending up with HBr and water because HBr is a stronger acid than hydronium. So the equilibrium is going to lie to the side of hydronium, and that's why we show water behaving as the base instead of bromide. All right, there you go. Now this is a mechanism I expect you to know. Okay, I do expect you to know all of the mechanism of enol formation and halogenation. But this is kind of a cool reaction. You just throw a bromine there at the alpha position. Pretty neat. Now, what would happen if you had an unsymmetrical ketone? Right, you can see that this ketone here, so this would be 2-methylcyclohexanone. In this compound, there's no plane of symmetry, right? So what would happen in this case, because now you've got the alpha proton that I'm highlighting in blue, and you've also got alpha protons, one of which I'm highlighting in red. Where does the halogenation occur? Well, the answer is it's going to occur at the more substituted carbon, which would be the carbon that has the blue proton on it. We're going to get some halogenation on the other carbon as well, but the reason why we get the more, or the bromination occurring on the more substituted carbon is because it proceeds through an enol. If you compare the two enols, which enol is going to be more stable? The enol that's possesses the more substituted double bond. It's going to be the more stable enol. And so this is the one that's going to act, I guess I should use a black pen here, but this is the enol that's going to act as the nucleophile, right, towards our bromine, Br2. Okay, that's just an abridged version of the mechanism here, but that's how it's going to react. Okay, so halogenation, whether it's with bromine, chlorine, or iodine, is going to occur at the more substituted carbon. Now, what else is cool is that once you've installed that bromine, chlorine, or iodine, right, all three of those atoms are good leaving groups. So it says here that alpha halogenation provides a neato two-step synthesis for the synthesis of an alpha beta unsaturated ketone. So you have your ketone here, here's your alpha carbon, here's your beta carbon, there's your unsaturation. That's why we call this an alpha beta unsaturated ketone. So it says besides pyridine, okay, you can also use potassium T-butoxide or lithium carbonate. So pyridine any one of these will work for the second step. So again, after the first step, you would end up with this intermediate. And if you're wondering about the mechanism, we're going to look at it in a second, right? And then in the second step, you're going to do a deprotonation, okay? Now, if you're wondering, okay, this is great. Yeah, I guess, I'm making alpha beta unsaturated ketone. Well, I'm here to tell you, my friends, the alpha beta unsaturated ketones, you ain't seen nothing yet. They're going to come up a lot in this chapter. Guaranteed they're going to come up on your final exam and they're going to come up on your quiz. So whenever you hear me talk about alpha beta unsaturated ketone, pay attention because it's very important in organic chemistry. Okay. Well, let's talk about another type of alpha halogenation reaction. And this is one of those reactions that I feel it's just best if you memorize it. You can go on the internet and probably find some information about the mechanism, and the sequence of the mechanism is shown here with no curved arrows, but this is called the Hell-Volhard-Zelinsky reaction. We usually just abbreviate it the HVZ reaction, and it just adds a bromine at the alpha position of a carboxylic acid. Kind of a neat reaction. The first step is that you treat the carboxylic acid with bromine and PBr3, which is phosphorus tribromide. Okay, and then in the second step, you treat that with water. Now, he puts some information in here again about the sequence of the mechanism. First, you treat it with the phosphorus tribromide and the bromine. It makes an acid halide, and then you have the enol and the tautomer here, and then that's going to act as a nucleophile. You can imagine. I mean, this is a mechanism that isn't even drawn in the textbook, but I know you could all predict what's happening here, right? That's going to act as a nucleophile towards bromine, like that. Okay, and then you treat it with water, and you've all seen the reaction of water with an acid chloride, right? We looked at that in chapter 20. So then it just blows it apart to give you the carboxylic acid, which is shown here. Again, it's one of those mechanisms I'm not going to ask you about, but it's kind of cool, and it really maybe will help the reaction to crystallize in your mind and help you to understand what's going on here. All right, so the Hell-Volhard-Zelinsky reaction. So alpha halogenation, not only can it be done under acidic conditions, it can also be achieved under basic conditions as well. And you can imagine that the enolate is the reactive intermediate, right? You deprotonate to make the enolate, then you've got a good nucleophile. It's going to react with your Br2, and there you go. That's it. You install like that. Okay, so now we've seen alpha halogenation in acid and base. The thing is, if you do the reaction in base, if you stop, or the halogenation won't stop here, right? Because you've got another alpha proton here, and if you're in sodium hydroxide, what's going to happen is another molecule of hydroxide is going to come in, and it's going to rip this proton off too, which will give you, kind of running out of space here, but you end up with this where you have the bromine, and then you have a negative charge here, that enolate, and then that's going to react too with another molecule of bromine. So it's kind of like a runaway train, if you will, and it just keeps brominating and brominating until all of the alpha protons are exhausted. All right. In fact, after the first bromination occurs, so once you make this compound, and this was on the last slide, I'm just redrawing it here. Once you make this compound, since bromine is electron withdrawing, right? There's a dipole going that way. Now, what that does is it renders this proton even more acidic, and it reacts even faster. So it's really tough to stop it. Okay, it keeps going. Now, if you're wondering, is there any synthetic utility to this runaway reaction, Mr. Dion? That seems kind of dumb. If it just keeps, halogenating it over and over and over. Well, the answer is yeah, it can be very useful. It's one of the most famous reactions in organic chemistry. It's called the haliform reaction, this one here. Because if you use a methyl ketone specifically, right? If you have a methyl ketone, that means that you've got three, count them, three alpha hydrogens, right? You've got 1, 2, 3. So what happens is that runaway reaction occurs, and in this case, after the first halogenation, you'd end up with this compound, right? Then it's going to do it again. Then you end up with this compound, I'm trying to draw quickly here. Okay, then you have 2 bromines. Then it does it again, right? Until you end up with all 3 hydrogens being replaced with bromine. So I'm going to put CBr3, right? Every one of these hydrogens has now been replaced by 3 bromines. Bromine is electron withdrawing. So now you've actually created, this is actually a good leaving group. Okay, this is a good leaving group. So now you literally just hydrolyze that in aqueous acid and boom, you make a carboxylic acid, the haloform reaction. So not only do you end up with the carboxylic acid and you end up, son of a gun, please don't delete all that I just wrote. Okay, there we go. It's not deleted. And I know it's on the next slide, but I want to talk about it myself. Okay, you end up with CHBr3, which is called bromoform. Okay, right, which is the analog of, you know, if you had CHCl3, you call that, for kidnapping, chloroform. Okay, all right. Anyhow, so that's called the haloform reaction. So if it was iodine, you'd form iodoform. If it's chlorine, you form chloroform. And if it's bromine, you form bromoform, the haloform reaction. The details are shown here of the nucleophilic attack. You make the carboxylate, and then of course, so after the first step, after everything that's step 1, you actually make the carboxylate. Okay, so I should add that here, and then you add acid to the carboxylate to make the carboxylic acid. All right, I should point out that when you form the CBr3 anion, it deprotonates that carboxyl and it generates the carboxylate. And this is actually what drives the reaction to completion, is the formation of the carboxylate. Right, this is a carboxylate. Okay, it's resonance stabilized. Anywho, there we go. So very useful reaction. Again, I'm repeating myself like an old man, but it only works with a methyl ketone. Don't be trying to do a haloform reaction with any other type of ketone because it won't work. Okay, so synthetically useful way to make a carboxylic acid from a methyl ketone. Remember, we learned how to make this. We talked about how to make that from a Gilman reagent. We talked about how to make that, you know, using Grignard chemistry. We could make that from, you know, a secondary alcohol, and we could oxidize it. So we've seen ways to make methyl ketones in this class, and now you know a way to take a methyl ketone and convert it into a carboxylic acid. So you actually lose a carbon, right? You start out with this carbon and this carbon, but you only end up with 1. All right, there you go. It says here that it only really works well if the other alpha carbon has no protons attached to it. That's true. That's definitely true. It would work best. Okay, I don't know why I keep skipping around here. Cha-cha-cha-cha-cha. Where am I? There we go. So that's a lot of information in mind. And now we're going to take a look at some practice problems. So this is question 21.8, comes straight out of your textbook. All it says is predict the major product for this transformation and give me a mechanism. Now I know you know what the answer is, right? You end up with an alpha beta unsaturated ketone in this case. Okay, but we want to try and draw a mechanism for this. So 21.8. All right, so what's going to happen in the first step? If we're treating this with aqueous acid, the first thing we're going to do is we're going to form the enol. So let's draw the steps that result in the formation of the enol. I'm going to draw my hydronium ion like that. I'm going to do a proton transfer like this. Okay, and then I'm going to draw the product of that proton transfer, which is going to be my protonated carbonyl. Now I've rendered the molecule even more reactive. So what am I going to do next? I'm going to rip off one of the alpha protons with the water that I produced in the first step. So let's draw this like that. And then a water molecule is going to take this proton like this. And then what do I end up with? I end up with this molecule. So I'll still draw the positive charge. Here on my oxygen, I have a negative charge here, and I'll draw a resonance contributor. I move these electrons here and these ones up here. And then what do I end up with? I have a beautiful enol. So there we go. So now that I have my enol, I don't know why I put it there, because technically this is my enol over here. Now my enol can act as a nucleophile to bromine, Br2. So let's draw, we've got bromine like this. So my enol is going to act as a nucleophile like this. And then I'm going to end up with this intermediate like this. So now I've got my double bond here like that. I've got my bromine attached over here. And then another molecule of water is going to come in. So another molecule of water is going to come in, and it's going to rip off this proton here. Remember, I'm in aqueous acid. So now I've got my, I've got my alpha bromo ketone like that. And then for the last step, to generate the alpha beta unsaturated ketone, you can probably guess what's going to happen is I have this proton here, which can be eliminated. So I'll draw it in blue like that. I'm going to draw my pyridine like this. So here's my pyridine molecule, which is a strong, not a strong base, but it's going to behave as a base. I'm going to pull off this proton, make the double bond. I lose it like that. And there you go. That gives you your final product, which is the alpha beta unsaturated ketone like that. And I would also have pyridinium. So I also end up with pyridinium hydrobromide. There you go. And that's it. So we end up with an alpha. So this is called an alpha beta unsaturated ketone. All right. And there's the mechanism of its formation. Question 21.9 just says identify some reagents that could be used to accomplish each of these transformations. So here I want to make an alpha beta unsaturated ketone so you can totally see where, where the retrosynthesis is taking us, right? We need to make an alpha bromo ketone like that. So that means we need to make a ketone. And again, we could just treat that with pyridine, lithium carbonate, or potassium T-butoxide, and that will give us the alpha beta unsaturated ketone. So how do I get how do I make the ketone, right? I need to make cyclohexanone. Well, there's not Avogadro's number of ways to oxidize this, but we can oxidize this using a Swern, Des-Martin periodinane, Jones reagent. I'm going to choose PCC because my students love it so much, and that will give us cyclohexanone. Then to do the alpha bromination, we treat it with a catalytic amount of acid, as we just saw, and bromine, and that is going to make the alpha bromoketone, like that. And then in the last step, we do the deprotonation. It could be pyridine, okay? And again, I'll put here, or it could be lithium carbonate, that was on a slide a while ago, or it could be potassium T-butoxide. Any one of those will work. All right, the last one, we have 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5 carbons. So we're going from 5 carbons to 5 carbons. No change there, but we're making an alpha beta unsaturated aldehyde in this case. So it's an alpha beta unsaturated carbonyl. So that means that in terms of our retrosynthesis, we're going to have this compound where we have an alpha bromoaldehyde like that. So what are we going to have to do? We're first going to have to oxidize that primary alcohol to an aldehyde. I'll use a mild oxidizing agent like PCC. That would give me the aldehyde. Then I treat it with aqueous acid, catalytic amount, plus bromine. That gives me the alpha bromo aldehyde. And then I'm going to treat that with my base. What do I want to pick? I'll pick pyridine again. Pyridine. And there you go. But again, you could use lithium carbonate or potassium T-butoxide. Either way, it's going to work. Next one says, predict the major product of the following transformation. Here we're taking the carboxylic acid, so this is cyclopentane carboxylic acid. We're treating with bromine and phosphorus tribromide, followed by water. This is called the Volhard Zielinski reaction, or the HVZ reaction. And what do we do with the HVZ reaction? We convert a carboxylic acid to an alpha bromo carboxylic acid. So literally, all you got to do is draw this. You've only got one alpha carbon anyway, and you just put a bromine on it like that. Now, if you want to try to memorize the intermediates or something, you could totally do that, right? Like after the first step, you know, what you actually end up with is this. So this is an alpha bromo acid bromide. That's what this would be called. This is an alpha bromo acid bromide. And that intermediate was shown on a previous slide. It wasn't identified as such. But then after you treat that with water, right, it just gets blown apart. So maybe I could use this here like that. Okay. Anyhow, again, the HVZ reaction. You need to know that you take a carbonyl, or sorry, a carboxyl, and you convert it to an alpha bromo carboxyl like that. And let's take a look at the next one, which is 21.11. We're starting with benzyl bromide, and we're adding a carbon over here. So for this one, I think I'm going to need a blank piece of paper. I'm going to go over to a blank sheet here. Go, and I'm going to make some room for myself. All right, so let's see. This is question 21.11. I'm starting with benzyl bromide. They've kind of written it in a funny way here. There we go. So we're starting with benzyl bromide, and I want to make an alpha bromo carboxylic acid. So what am I thinking? I'm thinking the HVZ reaction, right? Right. That's what I want to do, because in terms of my retrosynthesis, if I had this carboxylic acid, okay, then all I have to do is the Volhard-Zielinski reaction, and I make the alpha bromo carboxylic acid. So then the question becomes, you know, how do I get from benzyl bromide to over here? Because I need to add a carbon. Well, the best way for me to add a carbon to this and make it into a carboxylic acid would be to first treat it with magnesium in a solvent like diethyl ether, then treat it with carbon dioxide, followed by aqueous acid. And that's going to give me this compound where I have the first carbon, then I have a second carbon, and I have a carboxyl group like that. Okay? Then I'm going to take this and I'm going to do the Volhard-Zielinski reaction, which is first step is bromine and phosphorus tribromide. And the second step is to treat it with water. And again, this is the HVZ reaction. Now, there is another way to do this, right? There's another way to get from here to here. I think which is perfectly reasonable, especially based off of what we learned in the last chapter. And that would be to first treat it with sodium cyanide, right? Just to make the nitrile. And then you could hydrolyze that with aqueous acid and heat. That would work too. I'd say either one of those pathways to this compound, to this carboxylic acid, would be totally reasonable. Let's take a look at the next one. So this is 21.11, and this is B. So we have this compound, this primary alcohol, and we want to convert it to an alpha bromo carboxylic acid. So again, same thing we saw before. In terms of our retrosynthesis, what do we want to do is just practice on the HVZ reaction, right? We want to make this carboxylic acid because we know we could use the Volhard-Zielinski reaction to make the alpha bromo carboxylic acid. So to convert the primary alcohol into a carboxylic acid, all I've got to do is use some strong oxidizing conditions like sodium dichromate, sulfuric acid, and water. like that. And that's going to give me this carboxylic acid, like that. And then all I have to do is the HVZ reaction. First step, bromine and phosphorus tribromide, followed by the second step, which is treatment with water. And again, this is the HVZ reaction. Next question. Let's go back to the slides here. We go back to our slides for chapter 21. Is 21.12. It says predict the major product obtained when the following compound is treated with bromine together with sodium hydroxide, okay, followed by aqueous acid. So let me redraw that. So we'll say step 1 is bromine and sodium hydroxide, and second step is aqueous acid, right? This is the haloform reaction. What does the haloform reaction do? Okay, in the haloform reaction, what we do is we take a methyl ketone, just like this here, we treat it with bromine and sodium hydroxide, followed by treatment with aqueous acid, and we convert the methyl ketone into a carboxylic acid, like that. So it's going to be the exact same thing here. Now, the reason why this reaction works so well is because, again, you have the 3 alpha protons here, okay? So you deprotonate all of those with the sodium hydroxide. You replace each one of those with the bromine, and so you get this intermediate. Let me use my black pen again. But you end up with this intermediate where you have carbon with 3 bromines attached to it, right? This, again, is a good leaving group. So now you've still got sodium hydroxide in your reaction mixture, and the sodium hydroxide is going to come in as a nucleophile like this, produce a tetrahedral intermediate, which is going to look like this, CBr3. Then I've got my hydroxide over here. Then you lose the good leaving group like that. So you end up losing the CBr3 minus, and you end up with this. Okay, you end up with the benzoic acid, but then what happens is that the CBr3 minus is going to rip off this proton, okay, in the last step, okay? So then you actually end up, after step 1, with the carboxylate. So that's why you have to have the second step, where in the second step, when you treat this with aqueous acid, it just does a protonation, and you end up with the carboxylic acid, and of course you'd end up with water as well. There you go. So that's the haloform reaction. Very important reaction in organic chemistry. Extremely important reaction for all organic chemistry students to know. So what I'd like to do now is to take a short break, and I would like for all of you to try questions 21.13, and we're going to take a look at parts A and part D when we come back.